Alrighty, we are going to look at an example of looking at some critical points for a function. And we're going to use the derivatives. In our example, our function is f of x is ln of x squared plus 1.5x. So we're going to use the derivatives, find the critical points, and look at what that entails. So the first step, in order to use the derivatives, we've got to find the derivatives. So f prime of x, apparently I'm using purple. Oh, let's not do that. F of x, f prime of x is, let's see, derivative of ln of something is 1 over that thing times the derivative of the inside, so times 2x, and we'll simplify this in a second. And then plus 1.5. 2x over x squared is 2x to the negative 1, right? Plus 1.5. F prime of x is negative 2x to the negative 2 plus 0. Right? Okay, so we'll go ahead and plug those into our calculator. I conveniently already have them there. I have, you see, f of x, f prime, and f double prime. Okay, and first thing I'm going to do is just take a look at the original function. Okay, interesting. Looks like I have a maximum right around here, right? And something like a cusp or an asymptote there. We can explore that here. So I might make kind of a guess. I'm going to say a maximum at about, I don't know, negative 1.5 or so. Okay? And then asymptote or cusp or something at 0, at x equals 0. Okay? So and let's look at that asymptote. Let's figure out if it's a cusp. Let's trace at 0. It's undefined. So it's not a cusp. It's some sort of discontinuity. If we trace really close to 0, like 0.00001, we get negative 18. Let's try 0.0000001. Closer to 0, and it keeps going down. Looks like it's a negative asymptote. Okay. Other thing I'll do before I really get into this is I might just zoom out real quick, unless you know for sure that this is all that's going on. And it looks like that's all it is. You know, you've got the features all right there close to the origin. You might want to look up further in the upward direction, but this is probably fine. I think we're pretty safe. Let's go back to zoom 6. Okay, and let's take a look at the derivatives. Now, the minimum should happen where f prime of x equals 0. We can use our calculator. You can check out, I just do one function at a time, usually, to keep things simple. It looks like it crosses 0. Maybe it's negative 1. Or, you know, maybe negative 1.5. I'm not sure. Can't tell. I could use the 0 tool, but you know what? This function, if I just take this and solve for 0, 2x to the negative 1 plus 1.5, you know, I subtract 1.5. 2x to the negative 1 equals negative 1.5. Divide by 2, and raise everything to the negative 1. So x equals negative 2 over 1.5, which is 4/3. So negative 1 1/3. So, you know, 1.5 wasn't too far off. But my minimum happens right here. Okay? And it looks like my original function is my first derivative is undefined at x equals 0, which confirms that there's, you know, an asymptote at 0. And let's just look at our third derivative for thoroughness here. We want to look for points of inflection. Okay. We see here it's definitely undefined at x equals 0. But are there any points of inflection? You know, does it cross the x-axis? Well, if I trace, and let's just move out here, you know, I can move out to the left, and I don't think this is ever going to reach the x-axis. It looks like we have asymptotes that just go out and approach 0. Okay, we could trace a, you know, 5 out that way, and 10, and, you know, you can keep, oops. 10, let's do 10. What's wrong with 10? I don't know. Let's do 5 again. 50, right. 5, okay. And then we can trace out, and you can go as long as you want, or you can look at a table. You know, it's never going to, let's go change by hundreds or something. Our table's probably just going to go so close to 0 as we go down eventually. You know, it's never going to go positive. So the second derivative is always negative. It never changes sign. So we don't have any points of inflection. We just have that asymptote. Okay? So, but it is at 0, so our guess is confirmed. Okay? So that's basically all our critical points. We might want to say asymptote at x equals 0 or something like that. I'm going to write out timelines for these because we need to know how to do those. This is not always necessary for this kind of problem unless you're specifically asked for. A lot of times you'll get these with drawings. We have our drawing on our graph if we want to take a look at that. Hello. Let's put the original function back in there. Okay, so we have our minimum. It turned out to be at negative 1 1/3, negative 4/3, right? And we have our asymptote at 0. Okay, so here at negative 4/3, it was a minimum. Okay, the first derivative was 0. And the first derivative is undefined because we have an asymptote, ASY is how I abbreviate it. After the minima, I keep saying minimum. That's a maximum. Not minimum. Okay, max. After the maximum, the function goes down, so the first derivative is negative. Before the maximum is going up, the first derivative is positive. And after the asymptote, it just goes up. Okay, it's positive. Okay, that's the timeline for the first derivative. Let's do the second derivative. X, f prime, double prime of x. Okay. Let's see. All we have really is our asymptote at 0 to mark on here. Beforehand, it's concave down, negative, and afterwards it's concave down, negative. So there's no point of inflection. Okay. If that was a change, if it was concave up on one side, you know, we could maybe mark that it was a point of inflection or something like that. But that's all there is to it. All right. See you next time.